So the first one, set up but do not evaluate an integral for the volume of the solid obtained by rotating the region bounded by f of x equal to 8x minus x squared. And g of x equal to 5x. And we're going to be rotating that around the x-axis. You don't have to draw a picture for this, so I'm going to do it without drawing a picture. And then I'll talk about how you would do it if you did want to draw a picture. I mean, it's not really different, just you can do this without drawing a picture. So again, we're trying to set up an integral for the volume of the region bounded by these two functions rotated around the x-axis. So I need to find where these intersect. So I'm going to set 5x equal to 8x minus x squared. I'm going to bring everything to the left. So I've got x squared plus 5x minus 8x equal to 0. So I've got x squared minus 3x equal to 0. So I've got x times x minus 3 equal to 0. So I get x equal to 0, and x equal to 3. You might want to draw it just so you can tell whether you're using the, what's what I'm looking for? Well, here's the thing. We know we're going around the x-axis, right? To be using the disk method, you would have to be flush with the x-axis, which would mean the x-axis would need to be one of your boundaries. It's not. Y equals 0 is not one of our boundaries. So we know we have to use the washer method. We'll also draw the picture so we can see it, but I really want to do it without drawing the picture first. So these are our limits of integration. And then we need to know which function is the outer function. So the outer function, which is the big radius, is the one that's going to be bigger between 0 and 3, the one that's further from the axis of rotation. So I'm just going to pick a point between 0 and 3, like 1, and see which one's bigger. F of 1 is 8 minus 1. G of 1 is 5. So the big radius is F. The little radius is G. So then, to write the integral for the volume is going to be pi times the integral from 0 to 3 of your big radius squared minus your little radius squared. Do be careful. You have to square them before you subtract them. It can't be big R minus little r quantity squared. It has to be r squared minus little r squared. So this is going to be pi integral from 0 to 3 of big R, which is again f of x, so 8x minus x squared quantity squared, minus the little radius, which is 5x squared. Sorry, 5x, and then the radius is squared, so quantity squared. Something to notice about this, or something to point out here, is that the problem said set up, but do not evaluate. Don't do work that you don't have to do, right? So since it says set up, but don't evaluate, I'm going to stop right here. I'm not going to multiply this out at all. I'm not going to simplify my integrand at all, because the whole point is just to be able to do the setup, not to be able to do any simplifying or evaluating. The one thing I want to point out is that if you did graph this, y equals 5x looks like a line that goes to the origin, and 8x minus x squared is a downward opening parabola. It also goes to the origin. We know it goes to the origin because, well, 1, you can plug in 0 and get 0. 2, you know that these intersect when x is 0. So they intersect at 0. They also intersect over here like at 3, comma, whatever. So this is a downward opening parabola. It's got to do something like this. And so we're looking for the region between these two functions, which is this region here. Clearly, the parabola is the one that's further away from the axis of rotation, and the straight line is the one that's closer to the axis of rotation in this particular example. Questions about this? Other side's already erased. Look at that. All right, well, if there aren't any questions, we'll do the other one, the other volume one. So this volume one, you definitely want to draw a picture. Basically, if your volume has more than 2 functions as its boundary, or two curves as its boundary, I really need to draw it anyway. So this function, find the volume of the solid obtained by rotating the region bounded by f of x equal to the natural log of x. So I'm just going to start drawing it. So here's f of x equal to the natural log of x, or y equals natural log of x. And then what else have I got? Y equal to 0, which is the x-axis. And then x equal to e, which is a vertical line. I should really find these points of intersection. Most of the time, they're going to be relatively easy, meaning we know that the x-intercept of the natural log function is 1, 0. I know this point here. Well, I know the x coordinate is e and the y coordinate is 0, so I know this point is e comma 0. And here, I know the x coordinate is e, and if I plug in e for x in the function, natural log of e is just 1. So a lot of times these problems are designed so that the intersection points are not hard to discover. Now here's the deal. We're taking this region and we're going around the y-axis. Okay, here's what that should tell us. We know our integral is going to have to be with a dy, which means our functions are going to have to be functions of y. So before we do anything else, really, we should be like, hey, specifically this one here, we should rewrite this so it's x as a function of y. So you can say, right, I mean, you can do it the short way, or you can say e to the y equals e to the natural log of x. So we get x equal to e to the y. Right, but I really want to stress, if you're going around the y-axis, you have to have x equals a function of y. That has to be what is going into your interval. Okay, so just like before, our region is not flush with the axis of rotation, right? There's some separation. So we're going to have to do the integral of the big radius squared minus the little radius squared. In this problem, we're going around the x-axis here. The big radius, and I can draw my rectangle, right? Here's my rectangle. The big radius is that. It's e. Not e to the x, just e. The inner radius is the distance from the axis to this function. Now, it's not going to be the natural log of x squared. It's going to be e to the y on e squared. Also, this problem is much nicer this way because e to the x, or sorry, natural log of x is kind of a pain to integrate, whereas e to the x is pretty easy. We need to find the limits of integration. The limits of integration, so the radii are kind of given, or in this case, are the left and the right boundaries, whereas the limits of integration are the up and the down boundaries, and they're switched if it's the other way. If your region's this and you're going, this way, your limits of integration are, well, I should say your boundaries are the up and the down things, and your limits of integration are the left and the right things. So here, the lowest this can go is obviously 0. The highest this can go is the y value at that point, which is 1. So my limits of integration are 0 to 1. Okay, now we actually do have to integrate this thing. To integrate this, we're going to simplify it a little bit first. We're going to rewrite it as the integral from 0. Oh, what did I forget? I forgot something important. It's sometimes tasty.
Pie.
Right. Gotta have the pie. We'd be sad if we didn't have it. It's so good. So pi integral from 0 to 1. E squared is just e squared. And e to the y squared, it's going to be much easier to write as e to the 2y. So then we'll oops, 0 to 0? No, 0 to 1. So then we'll anti-differentiate this. The integral of a constant is just the constant times a variable. So you're going to get e squared times y. The integral of e to the 2y is e to the 2y divided by 2. From 0 to 1. Plug in 1. and you get pi times e squared times 1 minus e squared divided by 2 minus pi times plug in 0, and be careful here, you don't just get 0, you get e squared times 0, okay, that's 0, minus e to the 0, which is 1 over 2. So e squared minus half of e squared is half of e squared. So you get pi times e squared over 2, minus a minus is plus pi over 2. Or you can write it as one big fraction, pi times e squared plus 1 all over 2, if you prefer. Okay. I have to imagine there would be some sort of volume question. But, I mean, I could be wrong. You never know. Let's look at problem 3. Draw a phase plot for the differential equation dy dx. She would probably, I bet she would use dy dt instead of dy dx. It's okay either way. Dy dx equals y minus 1 times 3 minus y times 6 minus y. Okay, so when you're drawing the phase plot, it's very important to label the axes. So in this sort of problem, the horizontal axis is your y, and the vertical axis is your derivative, dy dx. This is a cubic function. We know how to graph a thing like this. We're just going to find the intercepts. So the horizontal, I'm trying not to say the x-axis because it's the y-axis. The horizontal axis intercepts are going to be the values of y that make this equal to 0. So y could be 1, or y could be 3, or y could be 6. Those are our horizontal axis intercepts. And then we just need to figure out kind of if we're above, where or above or below. Here you could find the vertical axis intercept by setting y equal to 0. If you set y equal to 0, you get -1 times, oh, I think -1 times 3 times 6, which is -18. It's not super important to be real precise here, but we can pretend like that's our point right there. So what's going to happen is we're going to come up, we're going to go through this intercept here, we're going to turn around, we're going to go through there, we're going to turn around, we're going to go through there. Right? All of these factors have odd powers, which means we cross the horizontal axis when we go through those intercepts. All right, so that's part 1 of the question. We drew the phase plot. Part 2, find all the equilibria, which we kind of already did, although we didn't say it, and tell me whether they're stable or unstable. So the equilibria are just the intercepts on the horizontal axis. So the equilibria here are y equal to 1, y equal to 3, and y equal to 6. And again, this is because an equilibrium is just where the function itself, y, isn't changing. Well, if y is 1, then dy dx is equal to 0 times 0. It doesn't matter, it's 0. And if the derivative is 0, that means nothing is changing. So these are all equilibria. Are they stable or unstable? This is where you don't have to draw the little arrows, but I like to draw the little arrows. So when the derivative is negative, it means that the y values go to the left. When the derivative is positive, right, we're above, the y values go to the right. When we're negative, we go to the left. When we're above, we go to the right. Okay, so 1 is unstable because, like, say if you started at 1.1, you would move to 3. 3 is stable because if you start either a little left or a little right of 3, right, you can't be way over here. If you started at 7, you're not going to move back to 3. But if you start just a little bit to the left or a little bit to the right of 3, you're going to get pushed back to 3. So 3 is stable. And lastly, for the same reasons that 1 was unstable, 6 is also unstable. If you start on either side of 6, you're going to end up moving away from 6. And then somebody asked me in the reflections, this question, which I thought was really good. It's a really good question. It's really easy to answer if you know how to answer it. So here's the part C part, the 3C. Suppose that the initial condition y of 0 is 5. The question is, what's the limit as t goes to infinity of y of t? Well, we don't. So you could. It is possible to solve this differential equation. You'd have to do partial fractions though, which no one wants to do. The more important thing is that we don't have to do solving. We don't have to solve the differential equation here. We can start. Well, here's the thing. This is the key observation. Oh, sorry, I used t. Sorry, I should use x. That's kind of a, yeah, I should. I'll try and change that later. Sorry, this should have been. Hopefully you guys understood what I meant. This should have been what's the limit is x goes to infinity of y of x. Okay. So here's the problem. Our graph doesn't have x on it, right? We're graphing the derivative versus y. What we're saying is y of 0 equals 5. So at time equals 0, I don't know how to graph that exactly, but what I know is that y is equal to 5. Oh, y is equal to 5. Well, that's right there. There's y equal to 5. Which must mean, yeah, sorry, I was about to go down here. Which must mean we're starting right here. Okay. Well, if we start at 5 and we're just on, right, we're not on this graph. That's not the graph we're on. We don't have the graph that we're actually on. But and actually, you could, sorry, just to kind of, yeah, we got time. Just to point out, right? We know that, right, you could graph y versus x and say that, okay, we know that 3 is stable and 1 and 6 are unstable. So like, here's y equal to 1, 3, 6. So if you start like between here and here, you're basically going to go up towards 3. Like that. Whereas if you start down here, you're going to be like, woo, away, or up here, woo, away, like that. So here's the thing. We started between 1 and 6. We started at 5. We're going to get closer to 3. Which you can totally see, right? If you start here, you're going to go that way, and you're going to end up at 3. So basically, if you start close enough to a point that's stable, you're going to end up getting to that stability. Right? So the limit as x goes to infinity of y of x, since we're starting at y equal to 5, has to be 3. On the other hand, if someone gave us a different, like if they said y of 0 was 7, then we're starting here and we're just getting pushed to the right forever. So then the limit as x goes to infinity of y of x would be, oh, sorry, I wrote this equal to 3, it should be the bottom part here, sorry. It should be, this is equal to 3. This would be infinity, because right, we're starting here, we're getting pushed that way forever and ever and ever. So hopefully that clarifies that a bit. And I think we're not going to have enough time for a tank problem, I'm sorry. I'll try and say something on a tank problem after I do this problem 4 here. Yeah. So let's see here. So here's the last one. That's dy dx minus x squared y equal to x squared. And here's the thing. You could have used an integrating factor here, but you also could have separated variables. So basically, if the coefficient of y and the function of x there are the same, you can say, oh, look, dy dx is x squared y plus x squared. And then you can factor out an x squared. Like that. You can also use an integrating factor, it's perfectly fine. It's just usually more work to use an integrating factor than it is to do separation. Most of the time, you can't do one or the other. Usually you're kind of forced to do separation or forced to do integrating factors, but there's a few that can be written in a way where you could do either one. So then we're going to separate the variables. We're going to bring the y plus 1 down to the bottom. So I have 1 over y plus 1 equal to x squared dx. We're going to integrate both sides, as you do. And let's see, we're going to get the natural log of the absolute value of y plus 1 equal to x cubed over 3 plus c. Also, we were given this condition that y of 0 equals negative 8. So now is not our moment to plug in 0 for x and negative 8 for y. We want to exponentiate both sides and drop the absolute value. So we're going to say e to the this, drop the absolute value, equals e to the this, which we're going to write as e to the x cubed over 3 times e to the c, but then we're going to replace e to the c with just, I usually use c, but I feel like Quran uses k. Maybe it's because her name starts with k, so like, yeah, k. Maybe not. So then, now is the time, now, or you can solve for y first. Now is the time to go ahead and plug in this information and say, okay, if x is 0, y is negative 8. So negative 8 plus 1 equals k times e to the 0. So it looks like k equals negative 7. So then we can rewrite this as y plus 1 equals negative 7 e to the x cubed over 3, and then y equals negative 7 e to the x cubed over 3 minus 1. Yeah, I will point out, if you keep the absolute value here, it can be a little bit problematic to figure out the right value of k. So it really is in your interest, even though it feels kind of like cheating, to just drop the absolute value. The constant out front here will take care of whether it needs to be positive or negative. Okay, what time is it? 58. I feel like there was something I want. So I will talk briefly about the tank problem, just to kind of give you guys, because I feel like there's a couple things that they're worth mentioning, and I can say them in a couple minutes. Sure. So let's say we have this set up. If you have to go though, I totally understand. You all are welcome to go at any moment you need to go. I will talk about this tank problem that I just made up. So let's say we have a 100 gallon solution, 80% bleach. That sounds really great. 20% water. And we are adding to it, we're adding a half bleach solution. So 50% bleach solution, meaning half bleach, half water, at a rate of 6 gallons per minute. So the idea here is that we want to set up and solve the differential equation. Okay, I'm going to do this probably faster than I normally would. So setting up the differential equation, let's so A of t is the amount of bleach at time t. So we want to set up a differential equation. The rate of change of bleach. Oh, sorry. We're adding bleach to 6 gallons per minute. We're also draining it at 6 gallons per minute. Right? We don't want to be increasing or decreasing the volume. That is almost always the assumption for these types of problems that we're doing, because we haven't counted the other kind. So the rate of change, so the amount of bleach going in, let's see. So how much bleach is going in? Well, I'm adding 6 gallons per minute, but only half of it is bleach. So the amount in is 3 gallons of bleach per minute, or 6 gallons per minute times, I guess the concentration is 0.5, right? I guess it's 1 gallon of bleach per 2 gallons of solution, right? You could do it that way. Anyway, yes, it's going in at 3 gallons of bleach per minute. How fast is it going out? Well, the concentration going out is not 1 gallon of bleach per 2 gallons of solution. It is the concentration of bleach, right? So the concentration of bleach is, I don't know, there's some amount of bleach per 100 gallons, because that's what the volume is in the tank, times how fast it's going out, which is 6 gallons per minute. That's right. The rate going in, 6 gallons per minute times 1 gallon per 2 gallons, which is our concentration. And then the rate going out is 6 gallons per minute times our concentration, which is the amount of bleach per 100 gallons. Okay. So there's our differential equation. We're going to write it as dA dt equals 3 minus 6a over 100. I actually don't want to write it like this, really. I really want a common denominator here. So I really want to write it as 300 over 100 minus 6a. Or I suppose I could factor out 100, maybe even 6 over 100, and write it as 6 over 100 times, say I factored out a 6 on top, so I'm left with a 50. Factor out a 6 on top. Typically, you want your a to not have a coefficient if possible. So rewriting this, I've got dA over 50 minus a equal to 6 over 100, which is 3 over 50 dt. Integrate both sides. Integral of this is negative natural log of the absolute value of 50 minus a. Integrate this, you get 3t over 50 plus c. Swap over the negative side, exponentiate both sides. You get the natural log of 50 minus a is negative 3t plus 50 plus c. Doing the e thing. Where's my other pen go? Sure. Doing the e thing, we get 50 minus a equal to e to the negative 3t over 50 times e to the c becomes our k. Now is the moment to figure out what your k value is. So your initial condition is that time equals 0. There are 80 gallons of bleach. Because 80% of 100 gallons is 80 gallons. So right now we're going to plug in 80 for A and 0 for T. So we're going to get 50 minus 80, so negative 30, equals K times e to the 0. So K. So K equals negative 30. So we're left with 50 minus A equals negative 30 e to the negative 3t over 50. Solving for A, I'm going to add A over here, add this over here. So it looks like A equals 50 plus 30 e to the negative 3t over 50. So there's a solution to our differential equation. The amount at time t is 50 plus 30 e to the negative 3t over 50. And that makes sense, right? Because at time 0, we're going to start off with 80, which seems reasonable. Okay, the last couple things I want to say about this, because there are two interesting questions. We could ask like how much you have at time t. That's not really interesting. The things I think people are kind of maybe struggling with here are the two following questions. What's the limit as t goes to infinity? And what's the equilibrium? Which, this was a question from the homework that somebody asked. The answers to those questions are the same, which is kind of, for these tank problems anyways, where the amount of stuff going in and the amount of, like the volume and the volume are the same. The equilibrium and the, I don't want to say this. Sorry, I want to say the right thing. Yeah, the equilibrium and the limit are the same. What do I mean by that? Well, what can I erase? Sure, I can erase this. I'll try to get this video posted as soon as possible so you guys can look back at it if you want to. So, let's talk about the limit. The limit, I erased the thing I didn't mean to erase. It's okay. So the limit as t goes to infinity of this 50 plus 30 e to the negative 3t over 50. Well, e to the negative, as t goes to infinity, t to the negative infinity goes to 0. So this part goes to 0, and you're just left with 50. Okay. Here's what I want to say before I talk about the other thing. If you've got this sort of system where the volume going in and the volume going out are the same, the limit of your amount of stuff is always going to be the value that makes the concentration in the tank the same as the concentration of the solution you're adding. We're adding a solution that's 50% bleach. And the limit of this is getting to 50 gallons of bleach in a 100-gallon tank. So, right, this is getting closer and closer and closer to being 50% bleach, which makes sense because if you keep adding something that's 50% bleach and taking out the well-mixed solution, eventually it's getting closer and closer to being 50%, and you keep adding the 60% thing. I know I erased my differential equation. Let's see if I can remember what it was. I'm like, no, I can't. It was dA dt equal to what? It was, I'm smart enough to figure this out. It was 3 gallons per minute minus A over T over 100 gallons times 6 gallons per minute. How do you find the equilibrium? You set the differential equation equal to 0. So we set this equal to 0. Again, I'm going to factor out my 3 over 50. Factor out 3 over 50. Yeah, I'm sorry. My math is getting a little bit crazy here. Oh yeah, I called this 300 over 100, sure. I guess I could just multiply, right? That would be smart. But I'm going to factor because I'm not that smart. So factoring out a 1 over 100 and a 3, you're left with, I feel like I did something very different this time. So I'm going to make sure I'm not making a stupid mistake. Sorry, guys, 1 second. 300.
You factored out a 6 before.
Thank you. What value of A makes this equal to 0? 50. So 50 is the equilibrium value. 50 is the limiting value. For these tank problems, the equilibrium value and the limit of the system as time goes to infinity are the same. And moreover, they are the value that makes the concentration in the tank equal to the concentration of the thing you are adding to the tank. All right, I think I've said enough.